So this is calculus section 6.8 on finding antiderivatives or finding these integrals. And our goal is to go backwards. We've been taking derivatives all of first semester, and we're getting into this concept of antiderivatives, of going backwards. Just like walking forward is usually easier than walking backwards. Walking backwards is a little bit harder, but there's a lot of reasons why we want to know how to find these integrals, from finding areas under curves to eventually finding volumes of shapes as well. So basic integration rules, the integral of 0 is going to be just a constant. The integral of a constant is going to be, you're taking it up a power to kx plus c. I can factor a number out front. So if there's some constant multiplied by a function, I can push it out front. I can split up the different functions of the integrand, either with adding or subtracting. And one we're going to see quite a bit is the opposite of the power rule. If it is a power, I'm going to raise it by 1 and divide it by that new exponent. So some of these things are going to become very intuitive to you. We'll look into some of the more complicated ones as well, but these are going to be our really basic ones. Starting with this example 1a, the integral of 3x dx. And in its most basic form, I'm asking myself, the derivative of what would be 3x? The derivative of what is 3x? Well, I know if I'm taking the derivative of something and it ends up as x to the first, it must have been an x squared. And when I take the derivative of this, I'd multiply 2 by whatever is out front, and it's supposed to end up as a 3. Now that 6th different property that I showed up here goes exactly through that one. So since I raised this by the power of 1, and it's now a 2, I'm going to take the 3 that was out front and divide it by this 2. And now as I think about taking the derivative of this, again, go backwards. What is the derivative of this? 2 times 3 halves, there's the 3. We would reduce this exponent by 1, which makes it become x to the first. The other thing with this is notice that these all have a little plus c with them. What that means is we could add any constant onto this, any number. And when we take the derivative of all of this, I already know that the derivative of any number is 0 anyways. So we're just saying plus any constant. These are called indefinite integrals because there's no lower bound or upper bound. So we're not actually looking at a shape, the area from this x value to that x value. We're just looking in general. So there is our first antiderivative in this section, our first integral. To the right, letter B. At first glance, I see a fraction. I'm thinking, oh, this is like using the quotient rule, low D high minus high D low, and I have to go in reverse on that one. That would be miserable. Thankfully, we don't have to do that. What we're going to do is rewrite this. It says 1 over x to the third. I want you to think, how could we rewrite this so it's just x to a power? What does it mean to be 1 over x to the third? Go ahead, take 5 seconds, talk to your friend, think about that. What would that be just as a simple x? Go. So how about x to the negative 3? I haven't integrated anything yet. I just put it into a form that's going to be easier to work with. Now, like we did in the last one, I'm supposed to take this and integrate it. This is supposed to go to a higher power. So what is 1 bigger than negative 3? Negative 2, right? We're going a smaller negative number, which is bigger. So add 1 to this, it's negative 2. And whatever this is, I'm going to divide by that or multiply by 1 over that value. This is kind of like the counterbalance here. And then plus the c. Ask yourself, if I took the derivative of this, does it get us back to x to the negative 3? The derivative of the c is just 0. The derivative of this, negative 2 times negative 1/2, that's positive 1, which is what we had up here. Reduce it by 1, there's the negative 3. All right, to letter C. Same idea. Take a quick 5 seconds again, compare your thoughts. The square root of x is x to the what power? So how about x to the 1/2? Now take it to the next step. Find the integral of that. So adding 1 to 1/2 makes it become x to the 3/2. Then I'm supposed to divide by 3/2. Dividing by 3/2 is a harder thing for me to think about. Dividing by 3/2 is the same thing as multiplying by 2/3. I think that's just an easier way to look at it, plus our constant. Now, this answer is fine. If it's free response, I'm done. More than likely, though, if you saw a problem like this on an actual AP test, and you might see something kind of like this, it would be multiple choice. And this isn't the way they would give it to you. Because the original problem was in radical form, we're going to convert this back into radical form. So x to the 3/2 means the square root, that's the 2 in the denominator, the square root of x cubed times 2/3, or 2 times this all over 3 would be the same thing, plus c. This is the more likely way you'll see it. Again, if it's my free response, if it's my free response, leave it like yellow. If it's my multiple choice, I'm probably going to go AP style and make you put it back into that radical form, which would be the circled one. All right, letter D. I'm going to pause for a second. I want you to think what we've done on these previous ones. Give you a good 30 seconds. See what you can do with this one. If you're looking at this one, you're saying, wait a second, something doesn't add up here. You have like you're right. If it's integral of 3x to the negative 1 dx, and I'm thinking of the power rules, what's 1 bigger than negative 1? 0, right? 1 bigger is 0, so I'd have 3x to the 0. Then I'm supposed to divide by that plus a constant. Well, what is x to the 0? Just 1, right? So now I have this weird looking 3 over 0, which I already know is undefined. There's no way that I took the derivative of any of this slop over here and it would turn back out to 3x to the negative 1. So this is a weird case, kind of. So I'm going to erase my blue. Actually, I'll just cross it off and say, okay, this didn't register quite right for me. Ask yourself, the derivative of what is equal to 1 over x? Do you remember? ln, right? So this is one of those special cases. So as I put these different things together, this 3 that's in the numerator, I can push that out front and just kind of forget about it. I could call it 1 over x dx, or I could put the dx in the numerator. It has the exact same meaning to it. So now this is a rule we just need to know. The integral of 1 over x dx is the ln of x. Absolute value bars around it because we can't take the natural log of a negative or even 0. The 3 still would go in front of it, plus a constant. So special case. The first 3 examples all dealt with the power rule, raising the exponent by a power of 1. In this one, we saw that that wasn't going to work out for us. We had to recall, yes, this is a natural log. So slightly special case. Let's go down to letters E and F. And in these problems, well, first of all, in letter E, I see we have a fraction. Again, my first thought is, oh no, I have to do the quotient rule in reverse. That could be miserable. I don't want to do that if I don't have to. But good news here is there's only one term in the denominator. And let me give you kind of a similar idea. If we had something like this, could we simplify this expression? What would it become? Right? Divide by 2, divide by 2. We can do that, right? We can divide both of those terms by the 2. We're going to do that in this problem that we're faced with right here. We're going to split it up. Instead of dealing with a fraction, integral of a fraction, I don't like. But what is x divided by the square root of x? In other words, x to the first divided by x to the 1/2. We subtract those, right? Wouldn't that be x to the 1/2? Think about that. X to the 1 divided by x to the 1/2. We subtract those exponents, we get this. Plus, turn to your friend or think on your own, what is 1 over the square root of x going to be written as? How about x to the negative 1/2? 1 over square root of x is 1 over x to the 1/2. Because it's in the denominator, we can call it x to the negative 1/2. So what we did in this problem, instead of trying to think about it as a division problem with integrals, we were able to divide each of those terms in the numerator by square root of x to get this. Now, I'm going to pause again, integrate piece by piece. Find the integral of the first, find the integral of the second. All right, first part. X to the 1/2 gets integrated. I'm going to use another nice power rule. Add 1 to that, so it's x to the 3/2 divided by 3/2 or times 2/3. Plus this next one, you add 1 to your exponent. Negative 1/2 plus 1 makes it x to the 1/2. Divided by 1/2 is the same thing as times 2 plus c. Now, a reminder here, the original problem started off with a square root in it, so it has the radical form. So I'm going to rewrite this as 2/3 x to the 3rd square rooted. There's the first part, plus 2 square root of x. That's 2x to the 1/2 plus c. Now it's in the same type of form as the original with the radicals rather than the power exponents. So 5 examples so far of different methods of integrating. Letter F is going to be our 6th. It says t squared plus 1 squared dt. Now I'm going to show you like my first thought on this one, and then we'll see why this wasn't a good way to do it and what's like a little bit off about it. So as I look at this right away, I'm thinking, okay, it's another power rule. This is being taken to the second power. So like all the other ones, what if I raise the t squared plus 1 to a higher power, which would be 3? I would divide it by 3 to cancel this out, or multiply by 1/3 and then plus c. I think upon first glance that the integral of this is this. Question mark, question mark, question mark, question mark. Is that correct? Well, how can we check that? Take the derivative, right? So the derivative of this, 3 times 1/3 is 1. That's great. Now t squared plus 1 reduces this to a power of 2. But there's more to the story, right? What else do you still have to do to find the integral of this part? Times 2t, chain rule, the derivative of the inside, right? And then the derivative of the plus c is there. Is this equal to what we were given? No. The chain rule is throwing this off a little bit. So my idea was a good idea. It just didn't work out. And that happens sometimes in math. There's nothing wrong with that. It just didn't work out. So erase, erase, erase. Or great idea. Minimize, throw it to the side. Sorry, can't do that. So another way. T squared plus 1 squared. Doesn't that mean t squared plus 1 times t squared plus 1? Is that too bad to multiply out? Like if this was to the 12th power, I would not want to multiply that at all. But t squared plus 1 times itself, wouldn't that give us t to the 4th? T squared plus 1 times t squared plus 1 to give us t to the 4th, plus what else? There's plus 2t squared, plus what else? Plus 1 dt. So now we're going to integrate piece by piece by piece. Take your time, turn to your friend, find the integral of each one of those pieces. So 1/5 t to the 5th plus it's t to the 3rd divided by 3, so it's 2/3 t to the 3rd plus what's the integral of 1 dt? It's t because we're integrating with respect to t, so plus t right? I'm making these all in terms of t. If it was dx, we'd have a different issue going on here. Good thing that these letters match up. This isn't my correct final answer because what do I have to consider at the very end of this? Plus c, plus some constant that might be in there. I don't know what it is. Maybe it's plus 0. Maybe it's plus the sine of square root of 3 pi or something really ugly. Any constant at the end that when we find the derivative of this, that c is going to drop off. So these are mostly power rules, with the exception of the ln. Think back to your other derivative rules. What is the derivative of sine? Cosine, right? What's the derivative of cosine? Negative sine. We're going backwards. What's the derivative of tangent? Secant squared. What's the derivative of secant? Secant tangent. So we're going to have to know those and be able to step our way backwards. Go ahead and scroll down a little bit. And we have this big chart corresponding left to right. I'm going to jump like somewhere in the middle and look at this row. What is the derivative of cosine? Negative sine. So what is the integral of sine? It's negative cosine, right? The derivatives of the cos were all negative. Now going backwards, the integral of sine has to be negative cosine. Why is that true? Well, ask yourself, what is the derivative of negative cosine of x plus c? Well, the derivative of negative cosine is negative cosine, or excuse me, negative sine, which gets us back to the original sign that's on the inside. So we really have to be thinking about how these negatives all play with each other. So we have like the power rules above this blue line. We have the trig rules between blue and yellow. And then we have some special cases below it. If the derivative of e to the x is e to the x, the integral of e to the x dx is e to the x plus c. We have an exponential rule, and we have a logarithmic. This is one that we looked at on the front side. So 3 kind of special cases over here to deal with some of those other ones. Eventually, we're going to look at a big formula sheet or a big chart that has a lot more on it as well. If you know your derivatives, the integrals are just walking backwards. Here we go. Example A, integral of 2 sine of x dx. Walk your way backwards. Let me give you 10 seconds. Confer with someone next to you or think on your own. What do you think is the integral of this? Once you have it, then maybe check to see if your answer is correct. Go.
No. Cosine.
Maybe it could be 3. I mean, 2/3 3 works.
Okay, here we go. Ready? Do we need to raise this to a power? No. If the derivative of sine is cosine, the derivative of cosine is negative sine, I don't need to worry about raising this to a power like we had on the front. Is the derivative of cosine going to be sine? No. What does it need with it? A negative. What else does it need with it? This 2 that's out front. Is the derivative of this going to be positive 2 sine of x? We have this negative 2. The derivative of this is, okay, the negative 2 is there. The derivative of cosine is negative sine times this. That turns it back into the positive. That looks good. It's indefinite. There's no bounds, so plus c. You've got to have that plus c on there. Letter B I'm going to do with you right away. This one looks miserable from the start because it's a fraction with trig functions. Oh, no. Let's put it into another form. This is some of our trig simplification. Sine over cosine squared. How about we split up that cosine squared that's in the denominator? So I could think about this problem like this. It's sine over cosine times 1 over cosine. That's what it is. Now thinking in terms of the secondary trig functions, how could we rewrite this sine over cosine? That is just tangent. And what is 1 over cosine? Just secant, right? We're not integrating it. We're just saying, well, this is tangent, this is secant, dx. And now tap into that reservoir of knowledge you have. The derivative of what is secant tangent, right? The derivative of our answer is secant tangent. What is our answer? Turn to your friend. Do you know this one? The derivative of what is secant tangent? The derivative of secant is secant tangent. So the integral of this is secant plus c. You've got to be able to think in reverse. You need to know those trig derivatives. Letter C, I'm going to pause, give you a chance to consider what do the implications of the 3 and the 3w have for this one. Can you find this integral?
Maybe. Let's think about this. How about the fact that, what if it was just 3 sine 3w? Okay, it's fine, it's 3 sine 3w.
I'm filling in some parts that I know. I know the derivative of sine is cosine. What should be the angle on the inside? I can't mess with it. It's got to be 3w because the 3w is there. So it's still a 3w. And then I have this issue of the 3 on the outside. What's going to happen with that? Well, if you found the derivative of this, would it get you up to that? Is the derivative of sine positive cosine? So the derivative of positive sine of 3w is cosine of 3w times 3, right? Because of the chain rule. So there is our integral. So that the fact that the 3 was already on the outside is actually kind of nice. It's taken into consideration when you took the derivative of this in the chain rule, it's going to pop that 3 to the outside. All right, to letter D. Again, I'll pause for a second, give you a chance to consider this one. Go piece by piece by piece.
Secant squared, we can do this one. Isn't that just secant tangent? No, secant squared is just tangent. Okay, so it's tangent. So it's
Just
just
the derivative of tangent.
or tan theta, whatever, I'm doing x.
Tan theta.
Okay, and then 3 secant tangent. Secant tangent is something, right?
Yes.
Secant tangent. Okay. So would it just be minus secant 3w?
All right, so to check, the derivative of what is secant squared? The derivative of what is secant squared? Tangent. Theta, theta, d theta. That's all good. Minus the derivative of what is secant tangent? The derivative of what is secant tangent? Secant. Secant of what? Is the fact that 3 theta is in here and that there's a 3 on the outside up here, is that good for us? If you took the derivative of this, wouldn't that pop that 3 out front with the chain rule? So our final answer is tangent of theta minus secant of 3 theta plus our constant. There is our integral. All right, we've got 2 more examples in this 6.8 section. The integral of 3x squared e to the x cubed. And as I look at this part of it, the 3x squared in there might make it seem like this makes this problem way, way more difficult. In fact, because this is here, it actually makes this problem possible to do. If I think back to my derivative rules with e to the x, the derivative of e to the x is a nice and simple e to the x. But if it was e to the 2x, the derivative of this would be e to the 2x times the derivative of this exponent, which would be 2. So we have to consider the chain rule in this one. So now as I'm looking at what we actually have here, we have e to the x cubed that I'm looking at the primary integrand in here. The derivative of this is e to the x cubed, great, times the derivative of this exponent, which is 3x squared, which as it happens is what we have in front. So the integral of this one is e to the x cubed plus c. How do I know this is correct? It's because if I find the derivative of my answer, it should come out to that integrand. If I scroll to the right, we have some derivatives from first semester that we looked at a little bit that weren't hugely important in the derivative world because they didn't come up a lot. But when it comes to integrals, these are going to be very significant for us. So we have the derivatives of arcsine and arctangent, which are both quite significant. I'm not going to get into the derivative of arccosine or arccotangent because those have negatives and they're not as, like, we could use them just as well, but we'd rather work with the positive ones. The derivative of arcsecant doesn't show up a lot, but this is what it is. But I'm starring the first two because they are going to show up quite a bit. So in this first example that I see, it's the integral of 3 over 1 plus x squared. I don't have to do this first step, but I'm going to push the 3 out front, just kind of ignore it for a second, and then ask myself, what can I do with this? It's 1 plus x squared in the denominator, and when you have something like, let's say like this, I can't split it up and call this 4 over 2x plus 4 over 6. That is not true. It's nice if I could have like a simple fraction for each part rather than a complex one, but this is something we can't do. If there's 2 terms in the denominator, we can't split it. Likewise, we cannot split this one up. However, this meets the arctan. The integral of this is arctan of x with the 3 in front of it. And as always, when we're taking the indefinite integral, put a plus c at the end of it. All right, so now we're moving on to section 6.9, integration by substitution. Integration by substitution. Jumping into our very first example, it says find the integral of 2x times x squared plus 1 to the 4th dx. Now we saw one kind of like this in section 6.8. If I scroll back to the beginning of this, and early on we had this problem where we just squared everything out. We took the integral piece by piece. That was a good way to do that one. Because of the chain rule, we had an issue, and it wasn't too bad to square something like this. However, in this problem, I really don't want to multiply x squared plus 1 times itself 4 times and then distribute the 2x. I could do it that way. It would make it way longer than it needs to be. So we're going to do what's called a u-Substitution. The 2x is here, yes, but this is the part that is the most complex of it all. This thing is being taken to the 4th power. So what we're going to do is say, let's let u, some other variable, and u is the most common one that we see in math, let u be equal to x squared plus 1. Let u be equal to x squared plus 1. Anytime we do one of these u substitutions, the next thing we're going to do is take a derivative of both sides. The derivative with respect to x. Take the derivative with respect to x. So on the right-hand side, when we take the derivative of this with respect to x, it is very simply a 2x. On the left side, the derivative of u is 1, but we're taking the derivative with respect to x. So what are we really going to call this when we take the derivative with respect to x? I could call it u prime, but what's a more specific way of naming it? Wouldn't it be du over dx? And I'll say this next step is not technically mathematically correct. Algebraically it is. But then what I'm going to do is take this blue equation and kind of multiply both sides by dx to get this. So this is noticing that what we have inside of the integrand has something to a higher power, and there's something else outside of it, and bring it back together. So recognizing this pattern is going to give us an idea how to do this integral. So it's the integral of, this was in the original problem, this yellow part that I've highlighted, but now since I let u be equal to x squared plus 1, what can we call this whole yellow part? Isn't that u to the 4th? All right, that's what that yellow part is. I'll just go ahead and keep color coding. That's what that part of it is. Then inside of this integral symbol, there is a 2x and there's a dx. Well, after I made this u substitution, I took a derivative of both sides. What is 2x dx equal to? Du. So put that in there. The original problem was all in terms of x's. There's a lot of stuff, a lot of things going on. But now this integral I have over here is not that difficult. What is the integral of u to the fourth with respect to u? It is u to the fifth. U to the fifth divided by 5 or times 1/5 plus a constant. This integral is not that difficult. Final step in this one, because there is no u's in the original problem, I'm going back to my let statement where I see this u at. The u is really x squared plus 1. I'm plugging it back in there. And this is supposed to be taken to the fifth plus c. I believe that is my correct answer. If I have time and I want to check on my accuracy, how could I see that this is correct? Well, take the derivative of it. If you took the derivative of this, would it get you back to this original integrand? So 5 times 1/5 is 1. You're taking x squared plus 1 and reducing it to the fourth power, which is up here. Chain rule, take the derivative of the inside. There's the 2x that's out front multiplied by it. I'm feeling, yes, my check is complete. This is the correct integral. U-substitution. To letter B. We want to integrate this. It's going to be another u-substitution. The more you see these, the more you recognize patterns and so forth. I'm looking at this, trying to find the most complex part about it. 3x squared isn't bad, but then there is this whole thing, which is being square rooted, and I don't particularly care for that. So this is where the u-substitution is going to start. Let u be equal to x cubed plus 1. And then like we did in the last one, and then with the algebra, so I'm going to skip a step, we're taking the derivative of both sides with respect to x. The derivative of the right side is 3x squared. The derivative of the left side is du over dx, but I know I'm going to multiply both sides by that dx eventually anyways. So when I take the derivative of the blue, the derivative of the left is going to be just du. The derivative of the right side is 3x squared with the dx after it, which very conveniently is exactly what we have on the inside. So can you rewrite that original integral with this information? I'm going to highlight a little bit more in yellow. It's all of this stuff square rooted. So isn't that really u square root or u to the 1/2? That's what the square root means. And then this other stuff we have in there, thankfully it's in there. If it wasn't in there, we'd have some issues. Thankfully, the 3x squared is in there with the dx. Well, 3x squared dx is du. I like that because these variables are the same. If they weren't, but these are the same. So now we can go for the integral. Integrate u to the 1/2 with respect to u. How about increase my 1, so u to the 3/2? Supposed to divide it by 3/2, which also means multiplying it by 2/3 plus c. Yes, yes, yes. And u was not in the original problem, so I'll go back and say this is 2/3 of u of x cubed plus 1, right? The u to the 3/2 power. The original problem was in radical form, so I want to convert this to radical form, and might as well do it now. U to the 3/2 means that the u is being cubed. The over 2 means it's being square rooted plus a c. So again, starting to recognize some of these patterns, seeing how a u substitution is going to turn it into a problem that can be integrated kind of smoothly. To letter C. Option. I could distribute this out, but that would make it kind of miserable. 3 secant squared wouldn't be bad, but secant squared times tangent isn't anything that's familiar to me from my derivative rules. So I'm going to go back to u substitution. What should we let u be equal to? Don't copy this part down yet, but I'm seeing secant squared, and I think, well, maybe that's the more confusing part. What if I let u be equal to that? Then du is equal to the derivative of secant squared. First of all, with the power rule is 2 times secant to the first. chain rule, now the derivative of secant would be secant x tangent x, and that's not what I see inside of these parentheses. So I let u be equal to this, or I could have even just let u be equal to the regular secant, and I would have gotten all of this stuff, which still doesn't match up with what's on the inside. So my idea for my u substitution didn't work. It happens. This is what we want to let u be equal to, because truthfully, that is more confusing. It's more complex. It is a trig function plus 3. The plus 3 makes it radically different. Let u be equal to the tangent of x plus 3. Now run with that. We had our u statement. Always, after you've done that, take the derivative of both sides. So du is equal to secant squared x dx. The derivative of the plus 3 is nice gone. Now that you've seen two others of these, can you put all this information together and take that integral? So integral of, it says tangent of x plus 3. That's my u value. The secant squared x dx, that is my du value. So this is what needs to be integrated. U with respect to u. In the original problem, I wasn't thinking that this is going to be a power rule of any sorts, but that's exactly what it's turning into. The integral of x dx would be x squared over 2. The integral of u du is u squared over 2, or times 1/2, plus c. It's a power rule. Then with our substitution, it's 1/2 of u, that's the tangent of x plus 3, squared, plus our constant. How do I know this is correct? Well, if we take the derivative of this, it would get us back to that original integrand.